My name is Anand. So today we're going to study sorting algorithms, specifically insertion sort. As we know, there are various different ways to sort through different problems if using different algorithms, depending on the sizes of the. For example, take queues. If the size is big or a small size is small, we use different algorithms. Similarly, we use different algorithms for sorted and unsorted ways, as we know, because some algorithms take a lot of time and a lot of space in small problems. So without further ado, let's start insertion sort. So what is insertion sort? The idea of the insertion sort is similar to the idea of sorting the playing cards. It is a simple sorting algorithm which sorts the array by shifting elements one by one, following some of the important characteristics of the insertion sort. It is basically one of the simplest implementations. It is efficient for smaller data sets, but very inefficient for larger lists or queues. Insertion sort is adaptive. That means it reduces its total number of steps if given a partially sorted list. Hence, it increases its efficiency. It is better than selection sort and bubble sort algorithms. Its space complexity is less, like bubble sorting. Insertion sort also requires a single additional memory space. Although it is stable, it does not change the relative order of the elements with equal keys. For example, let's take this array. As we can see in insertion sort, we pick up the key and compare it with the elements ahead of it and puts the key in the right place. For example, in 5, 1, 6, 2, 4, and 3. 5 has nothing before it, so we don't compare it. So we take 1. 1 is compared to 5 and is inserted before 5. Similarly, 6 is compared to 5 and 1. And since it is greater than 1 and 5, it is not changed. Then we take 2. 2 is smaller than 6 and 5, but greater than 1, so it's inserted after 1. And similarly, this goes on. So, to properly understand insertion sort, let's take an example of this array. Unsorted array. So basically, we start by dividing the array in a sorted section and an unsorted section. We put the first element as the only sorted element in the sorted section and the rest of the array in the unsorted section. We take the first element in the unsorted section as the next element to be put in the correct position. We copy the element to be placed into another variable so it doesn't get overwritten, sort of storing it in a temporary location. If the previous position is more than the item being placed, copy the value into the next position. If there are no more items in the sorted section to compare with, the item to be placed must go at the front. See, so we had 2 there, 9 and 2. Since 2 is smaller than 9, we put 2 in a temporary variable and shifted 9 to 2's place and 2 to the 9's place. Then we take 7. We compare it to 9 and it is smaller than 9. So the item is sorted section is less than the item to place. The item to place goes after item in the array. Now we take 5. 5 is smaller than 9. We shift 9 to 5's place. Compare it to 7, and 5 is smaller than 7, so 7 is shifted to 9's place. When compare it to 2, but 5 is obviously greater than 2, so we place it in place of 7. So now the sorted section is 2, 5, 7, and 9, and the unsorted is 1, 4, 3, 6. Then we take 1. 1 is compared with 9, then 7, then 5, and then 2. Since it is smaller than all of them, it is placed before 2. Now we take 4. Similarly, 4 is compared to all of them. Since it is less than 5 and greater than 2, it's placed after 2. Similarly, 3 is compared. And finally, 6. Since all elements have been sorted, we finally get a sorted array using insertion sort. Basically, the way of working of insertion sort is select, compare, shift, and insert. So now we have pseudocode for insertion sort. We start from I0 to n minus 1, less than the size of the total array. We take a counter j, that is 1, while j is greater than 0 and aj is less than aj minus 1. So basically, if the element that we are comparing is less than the previous element, we swap them and we decrement j. This is the code for insertion sort. This was the pseudocode and this is the proper code for insertion sort. Now let's talk about insertion sort in a linked list. So we take two, current and the insertion pointer. We let the current be on the first element and insertion point. So we compare 3 with 4. Since 3 is smaller than 4, we swap it. 1 is less, 3 is 1, 3 is greater than 1. So we swap 1 and 3. Now we go to 4, since 1 is the smallest element. When 4 is greater than 3, we swap 3 and 4. Now we compare 5. 5 is greater than 1, so we don't change it. 5 is greater than 3, so no swapping. 5 is greater than 4, so no swapping. Then we go on to 7. 7 is greater than 1, 3, 4, 5. So basically, I sorted it. There are best times to use insertion sort, and these are when the data sets are relatively small or moderately efficient. When we want quick, easy implementation, we don't want to code hard for insertion sort. When the data sets are mostly sorted already or partially sorted arrays, like the one in the given below, 1, 2, 4, 6, 3, and 2. So now on to the worst times to use insertion sort. When the data sets are relatively large, because the running time is quadratic, so it will take a lot of time and a lot of space. When data sets are completely unsorted, absolute worst case would be reverse sorted, because we have to compare each element and then swap them, so it would be a disaster to use insertion sort. There are certain advantages to using insertion sort. Good running time for almost sorted arrays is theta n. A simple and easy implementation. It is stable, that is, does not change the relative order of elements with equal keys. As with everything, there are advantages and disadvantages. It is a lot less efficient on lists containing more number of elements, that is, large lists. As the number of elements increases, the performance of the model would be slow. Insertion sort needs a large number of element shifts, n to the power of 2 by 2, in comparisons and worst and average case. Comparisons. Let's compare it with different sorting algorithms. Let's start with the bubble sort. Comparisons with the bubble sort. In it, we set the largest element at the end in each iteration. Time complexity. The worst case, we have to do n comparisons for first iteration, n minus 1 for the next, and n minus 2 for the next until we reach at 1. Time complexity is O to the power of n squared. The best case, when the list is already sorted, we have the time complexity of O n. Average case, time complexity is O n squared, because we don't always get a sorted array. And let's move on to selection sort. In selection sort, the minimum element n, the whole list will be placed at rightmost. The worst case time complexity is O n squared, because we have to traverse the whole list. The best case, even the best case time complexity is O n squared, because swapping will happen at least one time. The average case is time complexity of O to the power n squared. Time complexity. The worst case. Comparison with the merge sort. In merge sort, we use divide and conquer. We divide the array recursively until it reaches one element, and then it gets sorted according to comparisons and then gets merged again. There's the code for merge sort. Now for the time complexity. In the best case, time complexity is O n log n. The worst case is n log n. So the average time complexity is again n log n. Because we are dividing the array in this case, for example, if we have 32 elements in array, then we will have to divide 5 times. So it will take log n times for dividing and n times for merging. So the total is n log n. I hope that with this presentation you were able to understand what is insertion sort and how to use it and when to use it and when to not to use it. Thank you.